Hello, I'm Dr Roo, and this is my review of GCSE level number theory, the first of 3 30-minute parts. We're going to work the theory of numbers from the ground up, so we'll assume at the outset that we really know very little, thus you need to pretend at this stage that you don't know what numbers are, have no idea how to reckon money, etc. We will assume you have some experience of the world though, from which you have some intuitive ideas. We keep our reliance on these to a minimum and develop our mathematics using definitions of new ideas which connect the other ideas together. These are formal definitions and theorems as opposed to the intuitive ones. The single most important theme of mathematics is that the network of connected ideas is consistent. If we have a problem and can arrive at a solution to that problem by following different paths through the network of connected ideas, then the solution must be exactly the same regardless of which path we follow. Be warned that, like most works of mathematics, this one starts off very slowly and then accelerates very rapidly. You need to stay on your toes to not get left behind, and if you do, then just rewind back to the last place at which you had full understanding. In any case, you should watch it through a few times until it feels familiar. So, without any more ado, let's get going. Maths begins with the intuitive idea that all things can be regarded as being part of some collection or set. There are a set of keys on this keyboard, a set of books on my bookshelf, a set of pens here, a set of paperweights. You get the idea. It's a point of curiosity that in the Oxford English Dictionary, set is the word with the longest definition of all the words in the English language. But in maths, it has the shortest definition, none at all. This is why I refer to the idea as intuitive. It does not have a rigorous mathematical definition, but relies on human intuition, based on experience for its meaning. As a matter of communication, the things in sets are called elements of that set. Next, we have the intuitive idea that sets have sizes, that being the number of elements in the set. We intuitively know that this is a set of 4 pens. The human brain intuitively recognises 12 different sizes of sets. This is a peculiar thing. You immediately saw the 4 pens I showed you. But had I thrown down 13 pens, you would have needed to stop and take a moment to count them out. I now introduce the notion of set isomorphism. If we have 2 sets of the same size, then an isomorphism is a one-to-one identification of each element of one set with an element of the other. We shall see very shortly how important isomorphisms are in mathematics. However, I won't be formally defining them here as they're not on the school syllabus, but we'll use them extensively to explain how math works and to prove things. The reason you probably haven't heard of this before is that, practically speaking, the word isomorphic is synonymous with the word is. If A is isomorphic to B, then for all intents and purposes A is B. I'm now going to present a set of symbols which I scroll on paper and a set of audible vocalizations, and we'll construct isomorphisms with set sizes. We recognise that some sets have 1 item in them. We associate the size of this set with the symbol 1 here and the vocalisation 1. Similarly, we have sets with 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12 items. Those last 3 symbols, of course, have some structure to them which we will understand later in this review. The symbols are fairly standardised across the globe. Even in the Far East, Arabian digits, as these are understood and used in daily life. Of course, The vocalisations I made are understood only throughout the English-speaking world. So, I've given you three sets: the set of intuitive set sizes, a set of symbols, and a set of vocalisations. And by associating them one-to-one in the order I just presented them to you, I've constructed isomorphisms between the sets. And here the power of isomorphisms becomes clear. We can reason about one set of things by reasoning about another, more convenient set of things, i.e., I can talk about mathematical ideas and can write down a symbolic representation of those same ideas. There's one final intuitive idea we must lean upon before we embark on a full development of the theory of mathematics: disjoint sets. If I throw down a set of pens and start talking about ink pens and ballpoint pens, then there's obviously some muddy overlap in the ideas there, because ballpoint pens have ink in them. However, if I show a set of pens and a set of paperweights, there's no ambiguity. A pen is a pen and not a paperweight, and a paperweight is a paperweight and not a pen. The two sets are clearly separate. They are disjoint. And so it is that we use three intuitive ideas on which we develop all of mathematics: sets, set sizes, and set disjointedness. Let me first say that I will be referring to sets with very simple names, consisting of a single symbol and its corresponding vocalisation. These will usually be capital English letters. For example, I may refer to the set of pens as P and the set of paperweights simply as capital W. We shall denote the size of a set A, any set, whatever A happens to be, as hash A, hash of A, or mod A, like this. Of these, the latter modulus notation is globally recognised, though the hash notation is well known and frequently found in textbooks and works of math. The fact that parentheses after the hash sign are optional is frequently observed in mathematics. Wherever brackets are mandated, if their omission causes no confusion, then mathematicians will generally omit them, in the name of brevity and, by implication, clarity. This is another core theme of mathematics. The notation is as terse as it can possibly be, to be able to put big ideas across as quickly as possible. We see that we can make a new set, the set of all things that are on this sheet of paper. This is the union of the set of pens and the set of paperweights. It is written down as P union W, where we use a highly stylised, simplified symbol U to denote the act of union of sets. And so we come to our first formal mathematical definition: union of sets. The union of two disjoint sets is that set whose elements are all those of the first set, e.g. a pen, and all those of the second set, for example a paperweight. Note that this use of the stylised U is globally recognised and is used exclusively for this purpose. Two sets are considered equal if and only if the sets contain exactly the same elements. Note the use of only if here. It makes the if a stronger statement. Not only are sets equal if they contain the same elements, but sets must contain the same elements to be considered equal. Equality is denoted, again quite universally, with the equal symbol and vocalisation. Thus, to say symbolically that two sets A and B are equal, we write A equals B. We also use the concept to introduce new names. To wit, if A and B are two disjoint sets, we may call their union the set C and write C equals A union B as a matter of the definition of the symbol C. Now we can write down and prove our first mathematical theorem: the commutativity of union. Given any disjoint sets A and B, A union B is equal to B union A. And the proof of this definition is simply that the definition of union itself makes no reference to the order of the operands of the union operation. Now, as well as being a theorem, this also serves as a definition. Commutative means that a binary operation such as set union gives the same result regardless of the order of the operands. The following two theorems also define new terminology. Given any disjoint sets A, B and C, then the sets A union B and C are also disjoint. That's what's known as the transitivity of disjointedness over union. The proof of this again is, since the sets are disjoint, the set C contains no elements which are also elements of A or B, hence contains no elements of the set A union B. C is therefore disjoint from A union B. Given any disjoint sets A, B and C, then A union B union C is equal to A union B union C. Note how we use parentheses here to force the order of operations. On the left-hand side we form A union B and then take the union of the result with C, while on the right-hand side we form the union of B and C and then take the union of the result with A. The upshot of this theorem is that the parentheses are in fact unnecessary. We can just write A union B union C without ambiguity. It doesn't actually matter what order the sets appear in or what order the operations are applied in. And the proof of this theorem is that, once again, the definition of union makes no reference to the order in which the sets are mixed together. Hence the results are the same either way. And note that we rely on the transitivity of disjointedness over union to assert that all the unions involved in this theorem involve disjoint sets, as is needed for the various definitions to apply. Now, if two disjoint sets of the same size, then we regard the numbers representing the sizes as being equal. Again, the equal sign is used to denote this equality. Thus, whenever you see the equal sign, you have to understand by context, i.e. the previous definition of all the symbols that are in use, whether it stands for an equality of sets or an equality of size of set. Now, a number C is regarded as the addition or the sum of the numbers A and B if and only if, given a set A of size A and a disjoint set B of size B, then the size of A union B is C. And we can write this in symbols as C equals A plus B if and only if A is the size of A, B is the size of B, C is the size of A union B, where A and B are some disjoint sets. A concrete example is that 6 is the sum of 4 and 2, because the union of the set of 4 pens and the set of 2 paperweights gives a set of 6 things. The operation of addition is denoted with the symbol plus, again a universally understood thing. Given any set sizes A and B, A plus B equals B plus A. Proof of this: suppose that there are sets A and B such that the size of A is A and the size of B is B, then A plus B is the size of A union B by definition of addition. It's the size of B union A by a commutativity of union, and it's equal to B plus A, again applying the definition of addition. The proof of this theorem illuminates an important underlying theme of mathematics. Theorems are proven using only the strict definitions and already proven theorems which have already been laid down. Now, given any set sizes A, B and C, then A plus B plus C is equal to A plus B plus C. The proof of this is that A plus B plus C is the size of A union B plus the size of C by the definition of addition, is the size of A union B union C, again applying the addition definition, and that's just the size of A union B union C because the union operation is associative. That's the size of A plus the size of B union C, again applying the definition of addition, and applying the definition of addition one last time gives us that this is equal to A plus B plus C, as we were trying to prove. We omitted to define the symbols in that proof. Oftentimes, brevity leads to clearer understanding than outright precision in mathematics, and you can safely assume that the variables have the same meaning here as in previous theorems. This is common practice, and has the unfortunate consequence that when you pick up a new book or work on mathematics, you have to read it from the start in order to understand the symbology that's in use. At this point, it is worthwhile to form another isomorphism with the set of set sizes. We consider the set of movements towards the right along a line. A set size of 1 we associate with a movement of 1 unit. A set size of 2 we associate with a movement of 2 units, etc. We see immediately that these shifts span a number of intervals, and 2 consecutive shifts span 2 disjoint sets of intervals, such that the total number of intervals shifted over is the same as the size of the union of the 2 sets of intervals, i.e. the sum of the sizes. Thus, this isomorphism is in fact more than just an isomorphism of sets, but is becoming known as what is called an isomorphism of groups. We don't formally introduce groups here, they're not on the school syllabus, but suffice to say that a set and a binary operation, such as the set of set sizes and the operation of addition, may be considered a group, and an isomorphism between groups means that an operation on the set of one group, such as successive shifting along a number line, gives the same result when mapped to the corresponding operation on the set of the other group, such as adding set sizes together. Now we hit the first limitation of the mathematical system we are developing. What is 3 plus 10? In terms of shifts along a line, we see that we can designate a common starting point and then label all points according to the shifts away from the starting point. And we see simply that 3 plus 10 leads to a point which we haven't given a label to, i.e. symbol and vocalization to yet. But recall that the human mind isn't capable of remembering more than 12 things of a kind, so we don't want to go inventing new symbols, and we reuse what we already have. The number representing 3 plus 10 is literally called 3 and 10, which down the generations has come to be uttered as 13, and it is given the compound symbol 1, 3. We do the same plus 4 plus 10, 4 and 10 becoming 14, 5 plus 10 became 15, and then we've got 16, 17, 18, and so on to 19. Now before we go on, let's reconsider the symbology that we've already used. Instead of 11 and 12, we'll leverage the idea that these numbers are in fact 1 and 10 and 2 and 10. And that's why we gave them the symbols 1, 1 and 1, 2, according to the pattern we've now established. But we still use the special sounds 11 and 12 to speak of them. This is just historical baggage, we just haven't been able to shake off the habit. Now we consider where we get with 10 and 10. Instead of regarding this literally as 10 and 10, we, at least our ancestors, instead chose to regard it as 2 tens, which has come to be vocalised as 20, and as such is denoted 20. In making this leap, a new mathematical concept materialises: multiplication. We write C equals A times B if and only if C is the number we get when we add B to itself A times. This use of the cross to show multiplication is again globally understood, though in more advanced maths it is quite often used for other things as well. And other symbols are often used to denote multiplication. A dot is very common. However, remember what we said about mathematicians missing things out to keep the notation minimal, like brackets, if it does not cause confusion? Well, this is often exactly what happens with the multiplication sign, and we end up seeing C equals AB, which is understood to mean exactly the same thing that we wrote earlier. The simplest way to see multiplication is to view it as an arrangement of square blocks to make a rectangle, as shown for example in the case of 3 by 4. If the area of each block were 1 unit, then by definition of area, the area of this rectangle is exactly 12 is 3 by 4, as the rectangle has been constructed of 3 lots of 4 blocks. And this leads us directly to the proof of the following theorem, that given any numbers a and b, then a times b is equal to b times a, always. The informal proof of this is that the area of a rectangle does not change if it is rotated 90 degrees. This is an informal proof as it does not strictly rest upon only previous proofs and definitions, but involves a little intuition involving the concept of area of geometrical shapes, which we don't formally introduce as it does not fall in the subject matter of this review. We are happy in this case, however, that the concepts are clear enough to convince us of the validity of the proof and hence of the theorem. Note that the expression 4 plus 5 times 4 is equal to 4 plus 20 is equal to 24, i.e. we perform multiplication before addition. There's no new mathematical idea involved here, it's purely how the symbology is defined to work. It follows immediately that with commutativity of addition, we can infer that 4 plus 5 times 4 is just the same thing as 5 times 4 plus 4. We can now carry on with the systematic labelling of points on the number line. After 20, we go to, literally, 2, 10 and 1, which has become 21, then 22, 23, etc., up to 29, and then we get 3 10s, which has become 30, 31, 32, etc., 40, 50, 60, 70, 80 and 90, finishing the sequence at 99. By this time we've used all combinations of the 10 symbols available to us for labelling the numbers, and so we call the next number 100 and write it as 100, since it is literally 10 tens. Turning the crank we get 101, 102, 110, so on up until 999. And then we have 1,000, which is 10 hundreds, 10,000, 100,000, and then we get 1,000,000, and then it just gets a bit silly going on from there. But even if we're no longer interested in vocalising all the numbers, at least now we have a system by which we can write down any number, no matter, in principle at least, how large. Now, we've already seen 2 of the major themes in mathematics, such as using isomorphisms to reason about difficult things by reasoning about simpler things with a one-to-one correspondence, and using symbols in the most minimalistic way possible to convey mathematical ideas. Another great theme of mathematics is that wherever there is an idea, always think about the implications of turning that idea on its head. For example, we've learned that 4 plus 2 equals 6, but if we were told that something plus 2 was 6 and we didn't already know the answer, then how can we work out what the something is? We begin by defining a new operation which delivers the answer. C equals A minus B if and only if A equals C plus B. We note that the use of the minus sign for this purpose is globally recognised. Now we can see that x plus 2 equals 6 means that x equals 6 minus 2, just using that definition there. And we know the answer to be 4. Now there are 2 immediate points of note here. The first is that this definition seems very abstract, i.e. it's not connected with the intuitive idea of taking a set of things and removing some items from the set to leave a smaller set behind. And it's also abstract in that the definition does not actually seem to use any numbers. We could have given the example that 4 is 6 minus 2 because 6 is 4 plus 2, and then made a statement like 6, 4 and 2 can be replaced by any other numbers which sum together properly. But then why choose 6, 4 and 2? We could choose any symbols to stand in for those numbers, and that's exactly what we do in using A, B and C. Why A, B and C? Oh, you know, do, re, mi and all that start at the very beginning. Actually, quite a lot of textbooks would actually use X, Y and Z for this purpose. The second point about this definition is that you're probably wondering what the point is. We could only write down that 6 minus 2 equals 4 because we already knew the answer. Well, we now proceed to advance the theory of numbers and thereby discover ways that subtractions can be worked out when the answer is not already known. We start by looking at the isomorphism of numbers which shifts along the number line to give us a visual representation of this new operation, and we see that the operation of subtraction of numbers corresponds very nicely to shifting to the left on the number line. And now we have a visual method for working out subtractions, but we also have some new difficulties with the system of numbers. The first is, what is the result of 1 minus 1? This takes us to a point on the number line that has not been labelled yet. Of course, if you take 1 from 1, you end up with nothing, and we indicate this by literally drawing a circle around nothing to get the symbol we call 0, and which looks like this. And now we understand the symbols behind 10, 20, 30, etc. Literally, 30 means 3 tens and nothing. And what does 0 minus 1 give? Another point that needs a new label. We could choose 0 minus 1, but in the spirit of missing symbols out if the meaning is not lost, we omit the 0 and simply use minus 1 as the label for this point on the number line. And then following this template, we get minus 2, minus 3, etc. And keeping with this, we realise that we can, in theory, number every single point on the number line as far as we want in both directions. The set of all these points which so far labelled on the number line is called the set of integers. Now the German word for integer, or actually just number in general, is Zahlen. And so the set of integers is denoted with the symbol Z. Unfortunately, I is used for rather a lot of things in mathematics, so we use Z to avoid confusion. Note that many textbooks use highly stylized versions of the letter in the context of the set of integers, like these, but here we just keep things simple. Note that use of the letter Z to denote the set of integers is globally understood, but the letter is often used for other things as well. Context is important. Also note now that many textbooks define the set of positive integers as the natural numbers and denote that set with the stylized letter N, like these. Notice something else interesting that has happened here. We started with sizes of sets, constructed an isomorphism which shifts along a line, and then extended the concept by allowing shifts in the opposite direction. But in doing this, we have broken the isomorphism because we cannot now go backwards to the concept of set sizes. It is physically impossible to have a set with minus 1 things in it. Of all the underlying themes of mathematics, this is the one which probably gives the subject most of its power. Okay, so we now understand that the negative numbers are modelled by shifts along the number line to the left, and that positive numbers are modelled by shifts to the right. Addition of numbers corresponds to performing one shift and then another, and the single shift which gets to where you finished is the result of the addition operation. So for example, now we see that 6 plus minus 2 puts us in the same place as an original shift corresponding to 4. And so we see 6 plus minus 2 is exactly the same thing as 6 minus 2, using the operation minus. In this result, we understand the operation of subtraction. It is a shift in the opposite direction of that of the number being subtracted. If we turn this around and write 6 minus 2 is equal to 6 plus minus 2, we can then consistently give meaning to 6 minus minus 2, which is 6 plus 2, which is 8. So by now we've discovered all of the integers, sometimes known as whole numbers, along the number line, and the operations that relate them together. In the second half of this review, we will discover the numbers represented by all the other points on this line, i.e. the ones in between the integers.